our fourth masterclass in the masterclass series. Today I have with me Pugh from the Indiana Purdue University, Fort Wayne. Al is the emeritus professor and former dean at IPFU. He received a PhD in industrial engineering from Purdue University, and in his free time he instructs high-performance driving schools. Also, I did a little bit of research and found that Al is our longest continuous user of ExtendSim. So he's been using ExtendSim longer than anyone else has, other than those of us here at Management. So, Al, I'll send it over to you and be available for questions. Thank you.
Okay, thanks, Dave. I presume we're on, and I'd like to say welcome to everybody, and thanks for attending. Please forward your questions to Dave, and I'll continue to speak and then try to save some time at the end for questions. Matter of fact, there should be more than adequate time at the end for questions. The quality systems that I've chosen to talk about, I'm going to present in a very general way. That is, I'm not going to go into great detail about how to build simulations in ExtendSim. I'm actually going to try to make it as general as possible, so those of you who are not experts in ExtendSim can still, I hope, follow this lucidly. Those of you who are should be able to build the models, which, by the way, Dave has copies of, will be able to forward to you with relative ease. These are the topics that I'm going to talk about. The futility of attribute sampling, a pet topic of mine. Second one's going to be selective assembly, which is a very rarely used technique, but which yields itself to analysis using simulation rather well. Systems reliability, which most of you are probably familiar with, or at least have heard the terms before. And finally, quality of operations. The stance I'm going to take is that I want to use simulation models as a tool for exploration, persuasion, and training. And by persuasion, I mean to try to convince others that your plans are viable, to perhaps try to convince managers that your plan should be funded, and also to provide training for those people who are going to be using complex systems. Training can be extremely expensive, and simulation is not a bad way to start. One of the problems with quality systems is that most of the closed-form solutions, many of which have been around for almost 100 years, make assumptions about distributions which simply are not always accurate. And because of that, the results can be somewhat dubious. Modeling or simulating those problems with ExtendSim or other languages can allow you to use all sorts of non-standard distributions, that is, distributions based on your actual data, which can render the result much more robust and useful. Let's start off with one of my very favorite topics based upon Moore's theorem. That is the futility of attribute sampling. Attribute sampling means that articles or items that are exposed to the sampling plan are classified in two ways. That is, they're either conforming or not conforming, or good or defective, or whatever sort of binary classification you choose to make. It's also especially important to remember that this pertains to small lot sampling. And by small, I mean in the area of 50 items or less. That's a very subjective number, and it can get as high as 100, but more typically 50 or 30 is a more reasonable number. This kind of sampling occurs a lot in the area of the country that I'm from, which is the Midwest, where production for automotive industry is often done in very small lots. And so what happens is that this sort of sampling is often used. What Mood showed quite some time ago, many, many decades ago, was that there's an interesting characteristic about attribute sampling. Essentially, we're taking our lot of components, all of which can be classified good or bad, and we're breaking it into two sublots. One we call the sample, the other is called the unsampled portion of the lot, or the remainder of the lot, if you prefer. Mood proved that the correlation of the number of defective units in the sample is high, or is highly correlated to the number of defective units in the original lot. He also showed that that's true for the unsampled portion of the lot. That is, the number of defective units found in the remainder or unsampled portion of the lot is highly correlated with the number that were in the original lot. Well, look what's happened here. What's happened is that once I break a lot into a sample and the unsampled portion of the lot, what I really want to do is to pass judgment on the unsampled portion based upon the sample. Mood further showed that there is no correlation whatsoever between the sample and the unsampled portion of the lot. This is so counterintuitive to many folks that we had to resort to things like simulation, and not just simulation in software, but simulation physically, to try to convince people this is indeed true. And in spite of that, I go into one company after another and watch them try to apply it. Here's, if this is showing up, if the sampling rate is high enough on the screen, you're seeing a model in the background run which demonstrates Mood's theorem. It's fairly straightforward. I generate a lot of parts, or parts allocated into lots, I guess would be a better way to put it. I set an attribute. That is, I want to know if the lots, or if the components within the lot are classified as good or bad. I then extract a sample of a fixed size from that lot, put those both in queues, and then examine the remainder, or the items in the queue to see if they're conforming or not conforming. So essentially, I generate a lot, set a characteristic for each item in the lot, break the lot into two parts, determine if the item conforms, and finally, at the end, gather the statistics. This is the result of that simulation. Notice that there is an extreme, a perfect lack of correlation between the number of non-conforming parts in the sample and the number of non-conforming parts in the unsampled portion of the lot. That is, you can draw a straight line through here at almost any angle arbitrarily. There's clearly no one or strongest or best fit straight line. So if you would have very few non-conforming items found in the sample, you may have a lot, or very few found in the unsampled portion of the lot. The upshot of this is that attribute sampling in small lots is an absolute waste of time. Don't do it. It doesn't work. And I would be willing to wager that within the next 3 months, I will visit a couple of companies and find that they're applying it and that they think with great success. They aren't. It's just an illusion. Selective assembly is the second example I've chosen, and it is a rarely used technique because what happens is you have to apply it when process capability or your production capability is inadequate to specifications. And so you have to end up classifying parts and then combining parts or assembling parts within classes. For example, we have a piston and a cylinder, which is the example I'm going to use here shortly. What really happens is you have to classify all the big cylinders in one class and match them only with large pistons, because almost always the critical metric in such an assembly is not the size of the cylinder or the size of the piston. It is the clearance between the two. That is what really is important because it determines the performance of the entire engine. Matter of fact, it determines the reliability of the entire engine as well. This technique for pistons and cylinders has been applied in race engines for as long as I can remember, but there aren't very many race engines built. It is seldom applied to production engines, and the reason for that is our manufacturing facilities have evolved to be good enough that you don't have to worry about it. One of the downsides of selective assembly is it requires complete inspection of all parts in order to classify them. That has rendered it a very expensive technique to use until it's become possible to automate inspection, in which case this becomes a much more viable technique. This is a selective assembly model in which I create pistons and cylinders, and I assign size to them. And here you'll notice that I have a queue for pistons and a queue or buffer for cylinders. I only have one class here because I just have two queues, one for each of the kinds of components. I then assemble them, I calculate the clearance, I sort by clearance so I can get some idea of the distribution, and then I just split them, keeping components that are too big or too low. That is, those with negative clearance will clearly never be able to be assembled without extraordinary techniques, in which case you'll have a set of unusable pistons and cylinders. This is some detail, but the key point here is each classification, since I have a two-component system, will require two queues. If I want to add a second class, that is, say, big pistons and big cylinders, then I'll have to have two more queues. And you would continue to add pairs of queues as necessary to represent the number of classes that you want to build. As the number of classes grows, the number of components that actually are assemblies that will actually pass clearance specifications will improve. It's not a trivial function, and so it's best to oftentimes simulate this. And it's fairly easy to simulate. You simply add pairs of queues and sort as necessary. It's also want to point out that you have to be careful with these queues, because if they're sorted by size instead of just as they come in, then that sorting by size is in effect classifying everything as an infinite number of classes. So you want to make sure that you build these queues. They're not queues that are sorted on the attribute size. Some observations from running this model. A simulation model is really useful for determining the number of classes required to meet clearance specifications. As a matter of fact, it's one of the better techniques. To do this in an analytical way requires some very substantial math and some somewhat dangerous assumptions about the distribution of part sizes. Most everyone would assume it's normal. In fact, that's what most of the work has been done. But in fact, it's oftentimes not quite as normal as one would hope. As a matter of fact, one of the more common distributions for these sorts of things is a truncated normal. There are also other distributions as well. As soon as you start to change the distribution very much from the normal, these problems become mathematically intractable quite rapidly, especially since there are oftentimes multiple strategies involved for classification. And by multiple strategies, I mean, should you divide these components according to equal numbers per class? Should you divide them by equal width? That is, each class would go from maybe be a certain size characteristic wide, like 1/4 of an inch or 10/1000ths of an inch. There are many strategies that are employed. You can look them up in the literature. I published much of it myself. But the problem is that almost all the time when you start to deal with real systems of this kind, you have to simulate. Another advantage of simulation, especially simulation with a tool like ExtendSim, is you can easily add cost considerations. How much does it cost to inspect each part? How much does it cost to keep several buffers full of all sorts of parts? How much, in other words, the inventory cost over long term and short term? You can do that quite easily in ExtendSim. It becomes extremely difficult to do when you want to try to find a closed form solution. Matter of fact, to the best of my knowledge, no one has ever managed to accomplish it for any realistic system. I'm going to check to see my window here to see if I'm going too fast for folks. Don't see any hostile notes from Dave, so I'm going to keep on going. Systems reliability is actually my favorite example of how simulation can be very useful. And again, I'm going to show how it can be useful through the use of a very simple model. All the models in this presentation will be very simple. Real models get very complex, but they're also difficult to communicate in a short time. So I'm going to take a very, very simple system and take a look at how it might, or how often it might fail. Here I've got a simple system composed of only 3 components, cleverly enough called components 1, 2, and 3. Components 1 and 2 are linked in such a way that if either fail, some function cannot be performed. That is, they are linked in a serial way. The third component is connected in parallel with the first 2. Thus, the system will fail only, the entire system will fail only if either components 1 or 2 fail and 3 fails. In other words, failures should be relatively rare. Here are 2 possible diagrams. One is called the block diagram version of this. The other is called the fault tree diagram. Now, if you read a lot of text on this, you'll find that these are often called somewhat different names, or sometimes they use different shapes. But the general way of viewing this is this way. I prefer the block diagram when I'm first thinking about things, but it turns out that the fault tree diagram is oftentimes far easier to then match or map into a simulation model. So here are my 3 components. I start off here, I progress through this way. If 1 or 2 fails, the entire path fails. I then have to go through 3, but if 1 fails and 3 fails, the system fails. Or if 2 fails and 3 fails, the system fails. Sometimes it's easier to consider it this way. It depends a lot on how you first started to explore these systems. Again, I'm going to jump right into an example and actually assign values here. I'll consider the reliability R of a component as the probability of not failing. So I'm going to use historical data, or perhaps data supplied by the producer of these components. For example, if these are components like resistors, the producer can supply you with really robust data about what the reliability of that product is. So here I have a reliability of component 1 of 0.95, of component 2, 0.85, and a reliability of 3 of 0.90. What we want to do is determine what the reliability of the entire system is, because that's what really matters. Now, in order to do this analytically, we have to make the assumption that all the failure events are independent of one another. Think about how absurd that is. It appeals to people like me who are college professors. It probably does not appeal to anyone who has to build a real system that's going to work, because in fact these are not independent in the real world. We'll talk about that more in a minute. For my serial components, that is the 2 on top, 1 and 2, the reliability is simply the product of the individual components, or R12 is equal to R1 times R2, or about 80%. The overall system reliability can be calculated as 2 components, the R1, R2 merged, and R3. So we consider those that are in parallel, and you can see calculating the reliability of the system is somewhat more difficult, but not really that bad. And so I end up with a system, I would expect the system to be reliable about 98% of the time, or fail roughly 2% of the time. Let's see how we would simulate this. ExtendSim has some wonderful tools, because actually they have blocks that correspond directly to this. Here I have random values from an empirical table with 0 selected with R probability and 1 selected otherwise. That is 0 if it doesn't fail, 1 if something fails. I then match the first 2 through an OR block, combine the third one with an AND block to the result of the first 2. I then calculate some statistics on how they behaved, and then take a look in a display block about what those statistics are. I expected about 2% failure rate, as I recall. I ended up here with about 1.92. This was a relatively short simulation. That's not bad. The problem becomes in the real world that these three components may not be independent events. And you can think of several examples. For example, if one or two fails, that means everything that's going to succeed has to pass through component 3. It may cause the failure rate of component 3 to increase. Or all the components may be in some sort of box which is subjected to external stress of some sort, such as thermal stress, which will cause their failure rates to change, and even may change those failure rates in different ways. There's also cyclical stress, low cycle fatigue, all those sorts of things that you have to consider. So you can extend this model in a simulation model and relax the independence constraint fairly easily. That is not at all true when you want to try to find the closed form solution mathematically. When you relax this constraint, it becomes, shall we say, challenging. Still can be done sometimes, especially for the simple model. It can't be done for a very complex one. My last model, at least that I'm going to go over in any detail, talks about the quality of service. I have to confess, when I originally wrote this model for this presentation, that I chose a restaurant, so I called it quality of service, where a manager we could build a model of the restaurant and have several parameters which measure quality of service. That is, we can figure out how many customers come in, see the length of the line, and leave. We can take another parameter and say how many customers then do come in, wait in line, and find the line is moving slowly, and then leave. Or we can find how many customers actually come in, get through the line to the cashier, pay, and then wait in frustration, deciding never to return because they had to wait too long to receive their food. In fact, that model proved a bit too complex for a simple presentation like this one, so I decided to use a somewhat simpler model simply based on queues. And to tell you the truth, they're both real similar in the sense that human beings are wonderfully adept at considering mean performance, that is, average performance. They are remarkably dismal, I should say we are remarkably dismal at coping with variability. We just simply aren't good at it. Study after study after study has shown that humans are great at means, and actually so are many other animals. We're just disastrous at variability. And of course, variability is the key component here. Here's my serial production model. I have a couple of inputs, some of which you can fix, some of which you can't. One is process variability. That is, how long it takes to do each one of these three tasks. And I have both a mean, which I actually put here, and I have a variability, which is going to be global. One of the things now I put this as an input because oftentimes you can change this. That is, by improving the process in some way, you can, or the procedure in some way, you can lower the variability. That is one of the primary tenets, for example, of lean production. Continue to lower variability. It makes everything so much more predictable. One of the things that we can adjust on a shorter term is how many laborers I have. The outputs from this model, and there are many more I could consider, but I'm just going to consider how busy I've kept my labor and how much work is in process. And you can see these aren't necessarily related, or they're related, but in an inverse way. I can keep my labor very busy, but I may end up with huge work in process, large buffers for each one of these. So my labor pool can be assigned to any one of my three processes. Unit arrives, the unit may be an order, it may be an actual physical unit to do something with, and then it has to go through all three of these processes in serial fashion. So I've got process 1 that takes, on average, 2 time units, let's say minutes. Process 2 can be done quicker. And process 3 takes three full 3 minutes to dispense with. And then finally the order or item or unit can depart. Now, if I just base my analysis on means, which is a very dangerous thing to do, and I can probably take a pretty good guess at how much labor I'm going to require here. See, if this takes 2 minutes and units arrive every minute, probably if I have 2 people doing this process, or 2 workstations at this process, or 2 people at one workstation that can accommodate 2 people, however you want to model it. 2 would perfectly cover it. 1 should cover it here, and I'm going to require 3 here because it takes 3 times longer. For a total of 6. My labor requirements are 6. And that would work really well and keep labor 100% occupied, which, by the way, is probably in violation of many state laws. You have to have breaks here and there. But it would be very efficient utilization of labor. In addition, things wouldn't build up unless you consider that all of these have some variability. And then it becomes very difficult to determine how much labor you should assign and whether or not work in process will get to be unacceptably large. This is the ExtendSim model of my quality of service model. And I've tried to build the model in such a way, I know Dave gets upset at this because I never bothered to put these models in a straight line. But anyway, I'm trying to build my models in such a way that it actually physically represents the way my process is laid out. Here, parts arrive, they go into a buffer, and they finally get processed, and then they go into a second buffer for the second server, second activity, and then into the third process, and finally exit. And notice down here, I've used a feature of ExtendSim that is very useful. I have hidden part of this model in a hierarchical block. And I then have used animation tools in ExtendSim to show the key factors that I want to keep track of. And they're displayed right away. This is useful for 2 reasons. First of all, it gives some sense of what the model looks like in both in the way that my simulated model actually somewhat resembles a physical model. And you, of course, can easily add pictures to each of these so that they actually have pictures of the machine or activity at each spot. However, the hierarchical display is hidden in here, and this is the rest of the model, which is somewhat less comfortable to look at in the sense that it contains all the blocks I need to actually gather the statistics of interest. I like to hide these kinds of things. It makes the model easier to use, and ExtendSim is superbly useful at doing this sort of thing. Let's get to a summary of what this may look like, or some of the observations you can make in a model like this. For very low service time variability, the deterministic estimate for labor requirements suffices. That hardly ever occurs in reality. All processes have variability. You're lucky if they're small, but oftentimes you're not lucky, especially if it's a relatively new process and people are learning. Increasing the process variability increases the work in process and lowers the labor utilization, but these are not a linear relationship. This is how a tool like this can become extremely valuable when you're talking about training folks, to give them some sort of innate sense about the effects of variability. Now, I know it's a common fault among many managers that I have seen that they think they can reduce variability by simply yelling at laborers. In fact, yelling at laborers is not a method that's very effective, at least over the long time, for reducing variabilities. You need to actually critically take a look at how things are working, and more importantly, to understand that there is variability in everything in the real world. The third point I want to make here is hierarchical blocks are really useful for reducing visual clutter, and they can make the model much better as both a training and as a persuasion tool, because only the essential information is displayed. And of course, if you're curious, you can always click on the hierarchical block and open up the ugly details inside. Okay, time for me to check my messages again. It appears there are no threats or questions.
No questions so far. Feel free to type something in if you have a question, though.
I'll blunder on to the related applications for which I didn't write models, or at least I didn't put them in this presentation. But I want to talk about a couple of them that I found to be useful. One is a model that I built several years ago for, let's see, a large vehicle manufacturing concern. Big company, built vehicles. They had a database, and they were worried about the integrity of the database. Now, this was not a simple database. Database was quite complex, and they were making it increasingly more complex. The data not only contained information such as how long it took to do each sort of assembly operation and how many components of each type are required and in what order. In other words, a typical manufacturing database. But in addition to that, it contained artificial intelligence methods and expert skills so that it could optimize many of those things. For example, their final goal was to be able to go to a customer and log in remotely and say, well, if you want so many vehicles with this kind of engine and this kind of transmission and these other characteristics, here is when we can deliver it, here is the cost, and oh, by the way, the transmission you wanted with this engine is not viable because they simply can't be bolted together. Now, that's a very straightforward example, but it becomes much more difficult when you have things like multiple kinds of engines, all of which require a particular kind of engine mounting system, which may not be compatible with one another. So those are very, very useful things to do, but that sort of database is incredibly complex to build. So what happened is this database had to be constantly maintained. That is, you add things as new components and assembly procedures come along. You delete things to get rid of the old ones, and you constantly modify things as people find better ways to do things and quicker ways to do things and more efficient ways to do things. Unfortunately, every time a maintenance operation is performed, there was a small probability that they would introduce an error into the database. There are also applications taken from this database. That is, now we're going to actually use or inquire of the database an application of some sort that will tell me how to schedule and build a vehicle. Again, errors would crop up. Those get fed back into the database in order to update it. Hopefully then not subsequently changed by means. This turned out to be extremely difficult. And before they brought this new database online, what they wanted to do was to see if it was good enough, and they had a certain percentage error criteria for that, like 98.5, I believe it was, before they could bring it online. And they wanted to see if they were improving. It is really difficult to tell if you're improving. What they did is they took daily samples from actual production data, tried to apply it using this new database before it came online, and tried to figure out the number of errors. They also had people maintaining this database, and they would double check for errors here. So we had a bunch of experts overlooking this and who would pass judgment on whether or not these were errors. Once that was determined, we could then calculate whether or not the database was actually improving, and then we could use simulation to actually determine that given the current state of affairs and past state of affairs, when and if this database would ever get to the required level of integrity. Second application that is really easy to do in ExtendSim is something called bootstrapping or resampling in order to build confidence bounds. These two examples, by the way, are related in that this is how I actually used simulation to measure if this process was improving. By the way, the database was eventually accepted for production on schedule and has become very successful. And I cannot tell you the company for whom it's being used. Resample confidence bounds, or bootstrap confidence bounds if you prefer, is just a method of using a already existing data set in order to build some level of confidence about whether or not that those values are actually wildly variable or only minimally variable. The way that I have used this many times in simulation is to actually build a simulation so when products are being tested, for example, if this is destructive testing at the end of a elaborate production process, we don't want to destroy many more components than needed, since you can use resampling, and as you test the product, continue to add that. So it's almost a way of looking at this as a Bayesian problem, in that I have a certain confidence, given that confidence, and another piece of data, how much has my confidence changed one way or the other. This is an extremely powerful tool. It's easy to do and extend, but I couldn't, or ExtendSim, I should say, but I couldn't manage to come up with a very simple example that is acceptable for this kind of presentation. I think we're getting close to the end, so we'll have plenty of time for questions. These are some of a couple of conclusions. Simulation model is especially useful for systems that do not meet the statistical assumptions necessary, especially quality systems, to use more traditional quality methods. And that's, in other words, for almost everything, because it is shocking how many quality systems are based upon assumptions, for example, the constant use of the normal distribution, that may or may not be true. Oftentimes aren't. Your real data may not be as normal as you think. Simulation models can also give operators a feel for systems behavior, in other words, training, so they can get some idea of how complex systems are behaving and therefore make more reasonable choices in the allocation of resources. Okay, I've made that as brief as I possibly could to stay within Dave's 1 hour time limit. I'm more than happy to attempt to answer your questions. I should probably pop this window open to do so.
Yeah, there are some questions there. I think you can see them. If you can't, let me know.
Okay, good grief, there sure are. Should I just start from the top?
Yeah.
What's the biggest pushback from management when trusting a model? Well, the biggest pushback is always confidence. I mean, sometimes done in a somewhat hostile way. What you have to do is you have to include management people who are going to have to sign off on this thing from day one. If they understand and are confident about the assumptions you use in building the model, they're far more likely to accept it. At least that's been my experience so far. If you build a model off on your own, which many engineers like myself like to do, just go off in the corner and hide and build a nice model about something, it's going to be a really difficult sell unless you've actually gone through the difficulty of including those folks who may find the model useful right from the beginning. And that's a politically challenging thing to do, but you have to make sure that they're included from the beginning. Michael, Steve, what is the difference of small lot that Dr. Pugh mentioned under the definition of small lot? Actually, by small lot, I mean lots in a more technical way in which the hypergeometric distribution has not yet decayed to the binomial distribution. I'm sure that horrible mouthful sounded pretty gruesome. What it really means in the end is that probably if you're starting to get lots that are smaller than 50 and especially smaller than 30, you have a small lot. That's a nice easy rule of thumb to go by. Back to Brian. Okay, I'm glad things are okay. Michael, that base their pass rate on sampling 4 out of every 300 parts. That's a pretty strange sampling plan. I hope they had some justification other than historical perspective. Do you have a specific paper? Yeah, I'm going to send some more stuff today about the futility of selective assembly, but in general, Moore's theorem is very valuable, and even it was actually applied as early as in work by Walter Schuhart and Deming. Matter of fact, one of the so-called Deming criteria is based upon Moore's theorem. Deming forgot to mention that. It's the most politic way I could think of saying it when he first published it, but in fact it was heavily based upon Moore's theorem. And so you can look at some of Deming's work, remember to think back that it was Moore's theorem that he's following, and that's the best way to find it. As far as selective assembly, there's been a lot of work published, a considerable chunk of it by me a long time ago. It seems to me that most of the follow-up that I've had from that, and most of the questions have come in from areas of the world where production capabilities are not that great and where labor costs are small enough they can actually manually inspect every component. But now with automated inspection techniques, selective assembly can become a viable technique again. But again, you should only consider using it when you really don't have very good production techniques or methods relative to specifications. Examples might include some very difficult manufacturing things that go into satellites, which have incredibly difficult specifications to meet, and it simply requires a lot of oversight. Are you familiar with FDA requirement products that are simulated test data as opposed to empirical data? Only remotely, and so I prefer not to comment a whole lot on that. So no, I'm not familiar all that with FDA products, but I think I do want to address the fact that simulated test data can be combined with empirical data. Matter of fact, it's possible to base your simulation entirely on empirical data collection. That's what things like bootstrapping do. And so they are not necessarily entirely separate entities. Talk about normal distribution assumptions. You take pairs, triplets, or samples when you get the normal distribution. What happens is the central limit theorem will give you some indication of how large a sample it takes before you can safely assume that things are normal. Matter of fact, you can actually test that, and in most stat books you will find some formulas that will give you that information, and you can embed those formulas into ExtendSim using an equation block. Are there blocks specifically made for quality system simulation ExtendSim? Only the ones I showed you. In fact, I've never written more than 2 or 3 blocks that I've ever had to write more than 2 or 3 blocks to do quality system simulation ExtendSim. ExtendSim includes enough blocks that it's fairly easy to use the standard blocks, which is actually a good thing because writing your own discrete event blocks can be challenging, although writing your own continuous event blocks is actually fairly straightforward, just simply an equation block. Dave, feel free to jump in here if I'm insulting you in any way of my knowledge or sort of lack of knowledge.
Yeah, I kind of replied to him already, or I'm sorry, no, we really don't have any blocks for quality system modeling, but we really don't have any blocks for any particular kind of modeling. We just try to make the software as general as possible so that you can combine blocks together. And I did add a note that, of course, if you have a particular combination of blocks, you just put in a hierarchical block, throw it in a library, and then you've got it for future use. So that's kind of our goal, is not to be splintered through all these different kinds of modeling, but to provide something that we're not to say, okay, today we're going to work on quality modeling, and tomorrow we're going to work on reliability or on any particular area. We just are always trying to provide a general purpose. Kind of a long answer to the question. Sorry.
And I agree. Oftentimes you can save your own hierarchical blocks for later use. Let's see.
Actually,
Why is it that very often sick? I'm sorry.
Oh, I'm sorry. I was I was saying it was a good question from a boy is coming up. So.
Okay. Why is it that very often Six Sigma professionals depend upon traditional methods instead of sim models? You know, I don't know, because I have seen Six Sigma professionals use bootstrapping in order to minimize the amount of data they have to collect. But I think it's more a matter of just being familiar with how powerful a tool simulation can be. And I have advised Six Sigma professionals and worked with them using simulation, and many of them are actually surprised and pleased at how powerful a tool this is. What I would recommend you might consider is when you're doing Six Sigma analysis is to start off with simulation using actual data and then using bootstrapping methods to put a fixed confidence bounds about that data. It's actually a good way to introduce people to using simulation without having to bridge the fear that they may have about using simulated data, which can be quite scary to some folks saying. Matter of fact, my spouse is a sociologist, and she's constantly irritated by the fact that I generate enormous amounts of data with my simulation, and she has to go out and collect it, which takes forever when you're dealing with people. And so she's, I would almost say, envious of the fact that we can generate lots and lots of data with simulation. Is it possible to calculate resource utilization per product across various product portfolios in a quality inspection model of a manufacturing part? Yes. Can I do that in 5 minutes? No. But yes, it's certainly possible, and I have done similar things. There are some good tools here. Give it a shot. ExtendSim, I think, is relatively reasonably priced. And so it's pretty easy to start experimenting. I'm sure Dave would help you find that as well.
Yeah, I would encourage the asker of the question to contact us, and we'd be happy to explain how you do that. It would just be a matter of kind of subdividing as items leave a particular operation in the system, just tracking it, the amount of time spent on each item, and then calculating utilization. You can kind of slice and dice that sort of thing however you want it.
And you can keep track of items that are passing through a simulation. Each one can have multiple attributes, and you can easily take a look at those anytime you feel like it. And you can combine them in all sorts of things. It's a very powerful tool. I would encourage you to give it a shot, because it may very well be worth your time. It certainly has been worth my time. Actually, it's been worth my entire career. I've done nothing but simulation. Well, I don't see any other questions here, Dave. Do you? I should also mention that all the models, the 4 models I used here, I have sent to Dave and told him that he can share them with whomever he wishes. I don't make any guarantees that they're perfect, but you're certainly more than welcome to look at them.
If there's no other questions, Al, thank you very much. That was excellent. So thank you very much.
Thank you so much. I very appreciate everyone attending. Thank you for your time.
Thank you, Al. And if there's nothing else, I'm going to end the webinar.
Okay. Thank you, Dave.
Okay. Thank you.